Hey everybody, welcome back. For me it's been a little while, but last time we talked about external flows and gave a bit of an introduction into Fanno Flow, which is flow with friction. We essentially ended the last lecture discussing the Fanno line on the Fanno line, which is a line on an HS diagram of the following form. Where we can sort of write down the total enthalpy of the horizontal line on the top, and then there's this line here. It's of that shape. And we had two branches, one upper branch and one lower branch. The lower branch was supersonic, and the upper branch was subsonic. And we showed that really just through the way that friction operates in terms of generating entropy as the flow proceeds, that point on the right is a limiting point. And then at that limiting point, the velocity is the sonic velocity. So the Mach number is equal to 1. Okay, so that's where we left off, and we're going to go ahead and jump straight back in with the math. Okay, so let's start off by recalling the one-dimensional differential momentum equation. We talked about this in lecture 2. It's dP over rho plus the friction factor F times V squared over 2 dE. That's the effective diameter times dx plus G dz plus D applied to V squared over 2 equals 0. So like I said, that's the 1D differential momentum equation from lecture 2. If you want to go back, we will remind ourselves that F is that friction factor, that Darcy friction factor. It's equal to 4 tau wall, the shear stress of the wall, divided by rho V squared over 2. So that's the Darcy friction factor. It's a function of the Reynolds number and the surface roughness, or normalized surface roughness, epsilon over d. Okay, so you'll often see some charts for the friction factor. We might do some problems where you'll have to pull that value, and then the effective diameter is usually calculated in the following way, where you take 4 times the cross-sectional area and you divide it by the perimeter. Okay, so let's rewrite this equation in terms of m. Rewrite in terms of m. And the way we do that is just by introducing the ideal gas law equation of states, P equals rho RT, and also this relationship where we know that V is equal to m times the square root of gamma RT. Okay, for a perfect gas. And so if we plug that in, we get dP over P RT plus the friction factor F times m squared gamma RT over 2 dE dx plus G dz plus 2 gamma RT m dm plus m squared gamma r dt. Okay, that's just expanding out that total differential operator over v squared divided by 2 is equal to 0. And then we can further simplify this to write dp over p plus f m squared gamma over 2 de dx plus g over rt dz plus gamma over 2 d applied to m squared. That's gamma over 2 there. D applied to m squared plus gamma m squared over 2 dt over t is equal to 0. Okay? So let's label this equation with a star, because we'll come back to it. Okay, and then remember when we started treating Fanno Flow, we set the heat transfer in the active work or shaft work equal to 0, which means that the total enthalpy is constant, which means that because we have a perfect gas, that the stagnation temperature is constant. Okay, that classic chain of reasoning that we'll use over and over and over again. So then that means that if we look at the stagnation temperature T, Tt, and we write it using our standard relationship with the Mach number, where T is times this quantity 1 plus gamma minus 1 over 2 m squared. We're going to take the natural log of this thing, natural log, and then we end up with natural log of T plus the natural log of the quantity 1 plus gamma minus 1 over 2 m squared is equal to the natural log of some constant. Right? Because the stagnation temperature is constant. And then if we take the total differential of that, then we end up with this dt over t plus d applied to that quantity 1 plus gamma minus 1 over 2 m squared over that same quantity 1 plus gamma minus 1 over 2 m squared is equal to 0. And then we sub into star for dt, okay, dt over t rather. So that's what we want to do that right away, but that's where that's going to go. Okay, let's also look at continuity. Which, if we use our relations between the velocity and the Mach number and everything, it just tells us that p times m over the square root of t is equal to a constant. Okay, that's basically your rho v being constant, your mass velocity being constant, right? And so we're going to hit this guy with a natural log and then a total differential in the same way we did before. So just natural log plus d, just to denote what we're doing here. And that's going to give us dp over p plus dm over m minus 1/2 dt over t is equal to 0. And from there, we can solve for dp over p as minus dm over m minus 1/2 this quantity d1 plus gamma minus 1 over 2 m squared over 1 plus gamma minus 1 over 2 m squared. Okay? And so this is going to sub into star as well for dp over p. Okay? And then once we do that substitution, we're going to obtain, and there's some steps omitted here, what we end up with is f over dE dx is equal to gamma plus 1 over 2 gamma times this quantity d of 1 plus gamma minus 1 over 2 m squared over the quantity 1 plus gamma minus 1 over 2 m squared plus 2 over gamma dm over m cubed minus gamma minus 1 over 2 gamma quantity, or d of the quantity m squared divided by m squared. Okay? So then we integrate this thing. So again, just this will all make sense in just a moment. So we integrate from x1 to x2, so from two different points in the channel, in the duct that we have Fanno Flow, and you end up with f times x2 minus x1 over dE. The left-hand side is very straightforward, of course. And then you have gamma plus 1 over 2 gamma times the natural log of 1 plus gamma minus 1 over 2 m2 squared over 1 plus gamma minus 1 over 2 m1 squared, close bracket, minus 1 over gamma times this quantity 1 over m2 squared minus 1 over m1 squared. And keep in mind that this m1 and m2, these are what the Mach numbers are at locations x1 and x2 respectively. Because remember, the Mach number is changing as you proceed through the channel because of the friction. And the last term is gamma plus 1 over 2 gamma, natural log of m2 squared over m1 squared. Okay? And this equation is very important. It's essentially the way that you're going to relate the Mach numbers between two different points in a Fanno flow. Okay? One thing to note, though, is that in this derivation that we held f constant from x1 to x2, which is definitely not necessarily true, but something to keep in mind. And then, like I just said, this equation allows us to find m2 given m1 and a certain change in x beyond a certain point. So if you know what the Mach number is at a certain location, and you know you're going to move some amount of distance through a Fanno flow, then if you know what the friction factor is and the effective diameter, you'd be able to figure out what the Mach number is going to be at that distance. Okay? So that's good. You will actually use this equation fairly often, so but mostly in a table form, as we'll demonstrate in some of these examples. Okay, so let's look at the working equations for Fanno Flow. Make sure we keep our section highlighting going here. So, and let me note that this is we've used this term before, but this is specifically for Fanno Flow. Okay, so from the energy equation, we know that that HT and TT are constant, right? And that's like we said before, because there's no heat transfer or work being done. And so we can write the ratio of T2 to T1 just using that relationship between the stagnation temperature and the Mach number and the static temperature, where we'll just have the ratio of 1 plus gamma minus 1 over 2 m1 squared divided by 1 plus gamma minus 1 over 2 m2 squared. Right? This is just the same. This is the same as before. This is true for any system where you have let's say adiabatic no-work flow. From continuity, we know that rho v is constant, and remember this is because the area is constant. We've held the area constant for this type of flow for this analysis. So we know that rho 1 v1 is equal to rho 2 v2, and subbing in our relationship, our ideal gas equation of state, and our relationship between the velocity and the Mach number, we can obtain the pressure ratios by looking at P1 RT2 over P2 RT1 being equal to M2 square root of gamma RT2 over M1 square root of gamma RT1. And this thing really leads or yields P2 over P1 being equal to M1 over M2 times the square root of T2 over T1, which we can sort of sub in that thing there. And then this immediately gives us rho 2 over rho 1 as well, where we have M1 over M2 times the square root of 1 plus gamma minus 1 over 2 M2 squared over 1 plus gamma minus 1 over 2 M1 squared. Whoops. Okay, so you'll notice that the quotient and like this T2 over T1 quotient essentially just got flipped between those two. Just because that ideal gas law equation of state, that's all. Okay, so those are two more working equations. And then we can also look at the entropy. Right, so for entropy, we have that the change in entropy from states 1, 2 is equal to Cp times the natural log of T2 over T1 minus R times the natural log of P2 over P1. If we use that, or if we use the above ratios that we just derived for pressure and temperature, we can get that S2 minus S1, or the change in entropy, normalized by the gas constant R, is equal to the natural log of M2 over M1 times the quantity 1 plus gamma minus 1 over 2 M1 squared divided by 1 plus gamma minus 1 over 2 M2 squared. That whole entire quantity raised to the power gamma plus 1 divided by twice the quantity gamma minus 1. Okay? But we also know that PT2 over PT1 is equal to e to the negative delta s over r. So in addition to that equation, we also get that PT2 over PT1 is equal to M1 over M2 times the quantity 1 plus gamma minus 1 over 2 M2 squared over 1 plus gamma minus 1 over 2 M1 squared, with that quantity raised to that same exponent, gamma plus 1 divided by twice the quantity gamma minus 1. Okay? So that's our last working equation of that'll be useful to us. So with that set of equations, we can actually now solve for basically all the downstream properties once we're given M1 and delta X. So that's why we went through that painful exercise of deriving all of these, is because we just showed you how with that prior equation for F times delta X that we have boxed up here, if we're given M1 and an amount of distance down the channel that we'd like to travel, we can get the Mach number at the downstream location, and now we have the downstream properties in terms of the Mach stream of the ratios of the Mach number at the upstream and downstream locations. So we would have all that information. Okay, so these yield downstream properties. Props given M1 and delta X. Okay. All right. So now let's introduce another reference state. Okay. So this is not the sonic reference state. Okay. So I'm going to call it the star F reference state to show that it's for Fanno. Okay. In the book, this is not done, which I thought was a bit confusing. So I'm introducing this notation in the lecture so that it's at least clear here. But the definition is basically the same as the sonic reference state. So the star F reference state is the state reached when you adjust flow to m equals 1 along a Fanno line. Okay, so the sonic reference state, star reference state, was when you would adjust the flow to m equals 1 along an isentrope. Okay, or like you adjust the flow isotropically to m equals 1. This is adjusting the flow isotropically, or not isotropically, but to m equals 1 along a Fanno line, okay, which is not isentropic, right, because it says there's friction. So underline that, and then let's do some highlighting here. Organization purposes. Okay, so like I said, we're going to denote it star F. In the book, it's just denoted star. Okay, so and you're going to look up these values in tables. The table will be like a Fanno property table, but when you're looking for the starred properties, it's just going to be a star. Okay, but I figured I'll make that distinction, at least myself, just because it's a little bit cleaner. And then in a future sort of a open textbook that I develop for this course, I'll probably have that more clear notation in there. So let's look at the Fanno line again. Okay. So there's our standard Fanno line. We have our limiting point here. And the star reference lives, or at least the star reference lives there, okay? Or yeah, so this is the confusion. So let's say this is state 1, this is state 2. This is and it should say state 1 and state 2 are literally equivalent to location 1 and location 2. And this is where we're going to draw a duct here, and I probably should have done this even earlier to help with the confusion, because I've been talking about states and whatnot, and I think that it's important to realize that in Fanno Flow, states are just locations. So let's say that this is a Fanno duct. We have x1 and x2, and then at x1 the Mach number is m1, and at x2 the Mach number is m2, and then this is sort of like an actual, physical duct. Okay. And then the sonic reference state would be if we dropped ourselves straight down onto this line. So this would be 2 star, okay? And then this is 1 star. Okay, so those are the sonic reference states for those two thermodynamic states represented by the locations x1 and x2. And then the limiting point itself is the 1 star F reference state. So this is both 1 star F and 2 star F. Okay? And so what that looks like on this diagram here is if you had like a hypothetical duct that continued to the right here, right? So this is a hypothetical duct. Not real. But if the duct continued forward, you would eventually hit this point, which will denote X star F. And we know that M star F is equal to 1 by definition. Okay? So X star F is the distance you would have to travel for your flow to eventually reach Mach number 1 within a Fanno flow. Okay? So by using this reference state, we can construct Fanno table functions just like the isentropic ones, just by basically sending state 2 to be equal to star F. So in working equations, set state 2 to star F, and then you get Fanno table functions similar to isentropic tables. Like for instance, in isentropic tables, we'll relate between, say a certain point in the duct and the sonic velocity, which would be m equals 1. So then we plug in m equals 1 into the working equation, and the thing simplifies, and you end up with just something that's dependent on just the Mach number at that point. So, for instance, what you would end up in this case, so like if we want to look at T over T star F, this is just looking at the T2 over T1 relationship above. If we write this down, then you end up with 1 plus gamma minus 1 over 2 divided by 1 plus gamma minus 1 over 2 times m squared, and that's the m corresponding to the t on the top of left. And this is just a function of the Mach number and gamma, right? So this, when you go and look at your Fanno tables in the text, these are the functions that you would be seeing here, and they're just going to show up in the tables as p star or p over p star, but know that it's like our star F in our case. So 1 plus gamma minus 1 over 2 divided by 1 plus gamma minus 1 over 2 m squared. Okay, so you get the idea. You can look back at the working equations to see how that relates. And you could do the same thing for the rho and stagnation pressure relations that we did before. An important one to write down is this guy, where we have F times X star F minus X divided by the effective diameter is equal to gamma plus 1 over 2 gamma times the natural log of gamma plus 1 over 2 m squared divided by 1 plus gamma minus 1 over 2 m squared plus 1 divided by gamma times the quantity 1 over m squared minus 1. All right. And the reason why this one's important is because this X star F minus X, we call that Lmax. And the reason that we call it Lmax is because once the flow has been accelerated to m equals 1, it cannot proceed at the same, g or mass velocity to higher entropy, right? If it tries to follow that line any further, the entropy can no longer increase. So you've hit a limiting point. And so, a channel with a given surface roughness can only sustain flow with a mass velocity g up to Lmax. Okay. Beyond that length, the mass flow rate would then be limited to a smaller value, which would effectively move you to a different Fanno line. So we'll actually discuss the details of that at the end of this lecture. What we mean by that, it's called friction choking. Okay, so the appendix that has these tables is Appendix I in the text. Let's look at an example. So let's say that we have a converging diverging duct with a Fanno section at the exit. So this is state 1, state 2 is the throat, and then we have state 3. And then this goes straight off like that. And then at the exit of the Fanno duct is state 4. We'll say that our delta x is equal to 2.4 meters in this case, from state 3 to 4. And then our friction factor is 0.02. Okay, we're going to set the receiver pressure at 1 bar, and we know that P4 is equal to P receiver. Okay, we're also going to let the effective diameter be 0.14 meters, and then we'll have A3 over A2 be equal to 5.42. And then the question becomes, what is PT? That is the upstream stagnation pressure if the flow is all supersonic. Okay? So knowing what A3 over A2 is, so A3 over A2 essentially gives us the Mach number at station 3, which is 3.26, right? That's our third critical operating condition. And that's what we mean by saying is if the flow is all Mach number greater than 1. So we have that, and then from there we can get P3 over PT3 from the isentropic relations. This is 0.01853. And then P3 over P star F, okay, remember that's just a function of the Mach number at station 3, is equal to 0.1901. Okay, and we also know that fLmax, so what is this thing? L3max is the distance you would have to travel starting at point 3 to reach your limiting points in the Fanno duct. Okay, so fL3max is equal to 0.5582. Okay, so this is all just table lookup so far. So now what we do is we know what delta x is, right? So we can write fL4max in terms of fL3max and f delta x over d. I'll explain what I mean by that. So fL3max So fLmax rather is equal to fL3max over D. I should put a sub E on these. Minus F delta X over D. So why is that true? Well, like I said, L3 max is the distance you would have to travel starting at station 3 to get to the limiting point, right? And then the FL4 max is the distance you would have to travel starting at station 4 to get to the limiting point. But the limiting point is the same starting at both locations. So essentially what you're doing here is you're just saying the distance that I have to travel from 4 to the limiting point is going to be the same as the distance that I need to travel from 3 minus the distance I've traveled between 3 and 4. That's literally all it is. It's just a triangle inequality here. We set that equal to 0.5582 minus 0.36, and then that gives you 0.1982. And then we can take that value and from the tables get M4. So then M4 is equal to 1.673. And then that gives us P4 over P star F equal to 0.5243. Okay? And then we just need to take the values that we know and cancel them all out. So we know that PT1 is equal to PT1 over PT3. Everything's isentropic between points 1 and 3, so that's all equal to 0. Or sorry, not 0, it's equal to 1. And then you have PT3 over P3, we know that value. We have P3 over P star F, we have that value. And then we just found P star F over P4. And then we know what P4 is because it's the receiver pressure. And if you carry this all out, you get 20.5 bar. So that's how much the stagnation pressure has to be upstream to make this duct with this friction, or sorry, this nozzle with this frictional duct at the end of it operates basically at the third critical, supersonic throughout. Okay. Let's have so that's just one example. You'll do a couple more in your homework and probably see some Fanno Flow in your exam. So let's have a brief digression where we talk about Fanno Flow and its relationship to shocks. So it's a little interesting. So remember that that when we derive the shock relation, we use conservation of mass, energy, momentum. So to derive shock relations, used cons of mass, energy, and momentum. And this yielded the following 3 conserved quantities. So this yielded that the mass flow rate is conserved, that the across the shock, the total enthalpy is conserved, or in the stagnation temperature as well. And also, it yielded that this sort of P plus rho V squared was conserved. Okay, so this is true for Fanno Flow, and this is true for Fanno Flow, but this is not true for Fanno Flow because we have a friction factor in the momentum equation. So the conserved quantity that we get from the momentum conservation in the shock analysis is not conserved in Fanno Flow, and so for Fanno you get the following behavior, right? So the shock essentially has to jump between 2 points with the same P plus rho V squared on the Fanno line, and it has to jump to the same Fanno line because the mass flow rate is being conserved. So what do I mean by that? Well, let's look at for Fanno Flow, this quantity. So I'm going to plot a Fanno line or Fanno Flow for Fanno Flow. This quantity P plus rho V squared as a function of the Mach number. Okay, that looks like kind of something like an upside down parabola. Okay, and this minimum, that's a terrible, hold on a second, let me fix that. This will look a lot better. That's still not the best. So this minimum point is m equals 1. But if you start from a point here, say this is where your shock is going to occur, then your shock has to sort of jump over to that point there, where you have the same value of P plus rho V squared. So what does that look like on our Fanno line diagram that we've been drawing? It looks like this. So this is our HS diagram, and we have our Fanno line. It's not the cleanest Fanno line ever. So say we're starting here. This is 1, and this is state 2. So we're in the supersonic branch. You need to be supersonic to have a shock. And what happens is the shock process goes across like this to a higher entropy point, and then jumps on the same Fanno line to state 3 here, and then things proceed to sort of state 4 like that. So if I were to draw that in a duct, it looks like this. So you have flow coming in this way. This is our state 1, and then at state 2 we have a shock, and then immediately downstream of the shock is state 3, and then upstream of the shock we have supersonic flow, and then downstream of the shock we have subsonic flow, and then it proceeds. Here we have state 4. Okay, but the point that it's jumping to on the Fanno line is determined by this sort of conservation law for shock relations, where P plus rho V squared must be conserved across the shock. Okay, so that's the way a shock proceeds on the Fanno diagram. And we'll have some opportunity to talk a little bit more about the dynamics of shocks in this context later on. But to finish off this lecture, it's one of the shorter ones, it seems. Let's have a discussion about friction choking, which we alluded to before when we introduced the Lmax value or concept. So remember that we've talked about nozzle choking, right? So nozzle choking is when you lower the receiver pressure down to a critical pressure such that the flow in the throat is Mach equal 1. So P receiver lowered until flow in throat has Mach number equal 1. Okay, and then it can't be increased any further, right? Well, for friction choking, you have a given receiver pressure, and the rule is that you can add Lmax, or Lmax distance of duct can be added to the channel before it reaches m equals 1. And then any additional duct would require the flow to move along a different Fanno line. So it's like in this situation, you could add this much duct. If you want to add any more, you're going to have to go to a lower flow rate. Okay, so let's kind of draw what we mean here. So, and in fact, I should write that down. So friction choking P receiver fixed can add Lmax of duct to channel before M equals 1, any additional duct requires smaller G, right? And G was equal to rho V. So let's, like I said, let's draw this. So let's say we have like an upstream tank and then a Fanno duct. Spread these out a little bit, just to make the duct a little bit wider. So we have T1, P1, and V1 is equal to 0. So it's stagnant upstream. And then the start of the Fanno duct is 2. And the end of the Fanno duct, of the actual Fanno duct, is 3. Okay? And let's say that we added more duct. And we'll call that like state 4. So this is just more duct. What does that look like on the Fanno diagram? TS, which remember is equivalent to an HS diagram because we're talking about perfect gas here. Okay, so let's draw the stagnation temperature, which we know is actually equal to T1 because V1 is equal to 0. And we'll start there, right? And then we're isentropically accelerated through this converging nozzle down to state 2. Okay? And then at state 2, you are you start to travel along the Fanno line, and let's say that state 3 is exactly the limiting point for the duct as such. Okay? And so this is this has a certain G value here, and then when we added more duct, what we did was we required there to be a lower mass flow rate. And so we actually jump to a different Fanno line. So in that case, we have this 2' and 3' here, okay? And what it looks like here is we actually stopped earlier at 2' here. I should have labeled this 2 and labeled this 1. And then we jump onto a different Fanno line with a different G. This one has 3' here, and then, this guy goes down to here. Say that 4 is the limiting point for that Fanno line, and then this is G', and then we know that G' is less than G. Okay. So like I said, if you add more duct, you just are reducing the amount of the amount of mass that can flow through the duct in unit time. Okay, becomes choked. Okay, so one last little note here. What effect does extra duct have on a supersonic Fanno flow? So extra duct on supersonic Fanno Flow. And this is where it's a little interesting, where shocks kind of come into play. So let's say that we have a duct that's starting at M1 equal to 2.18. Okay, from the tables you get an fLmax over D of 0.356 in that case. And let's say that this distance between state 1 and this next state that I'm noting here, so this is n equals 1, we're going to say that that's Lmax. So say we traveled down the duct a certain amount of distance until we reached m equals 1, and then that was Lmax. And then if we wanted to add extra duct, what actually will happen is a shock will occur. And so if a shock occurs, so let's draw this situation again and say that we started at M1 equals 2.18 and a shock occurs. We know from the normal shock relations that M downstream of the shock is going to be 0.550. If we look that up in the Fanno tables, that gives us fLmax over D of 0.728. Okay, so what that tells us is that if shock occurs, it allows for over twice the duct length. Without having to decrease your G, or your flow velocity, right? And then if you add more duct, or if you want more ducts, rather, whatever, the shock moves upstream to higher M. Because remember, as you proceed through a Fanno duct, with supersonic flow, M decreases. Okay? So that's that little bit of a relationship between adding duct and the presence of shock or absence of shocks. All right, I think you'll have some opportunity to think about these things in more detail in your homework problems and perhaps on an exam. But yeah, if you have any questions, feel free to reach out. Otherwise, hope this one was nice and short and sweet and intelligible. Next time we'll proceed. I think the next lecture, if I'm not mistaken, I don't have it in front of me, will actually be focused on Raleigh flow, which is pretty interesting. So that means we're getting close to propulsion systems, which is where the rubber meets the rotor. I guess where the airfoils meet the atmosphere. That's pretty lame. Have a good one, guys.